Okay. All right, welcome back, folks. It seems we have lost our microphone again, so if you can't hear me, just let me know and I'll bring my voice up so you can hear me better. Okay. First things first, a few announcements. Recall that exam 2 is tomorrow, 6 to 9 in the Lake Room in the Union. If you have accommodations, you should have received an email from me confirming those and telling you exactly what to do. If not, then just let me know, and I probably have missed the email. Just let me know, and I'll take care of that today. Okay? So, as a reminder, recall the things that you want to focus on for tomorrow's exam. First things first is readers' behavior in readers-writers problem. So recall how the readers behaved. What did we do to allow multiple readers at the same time in the readers and writers problem? So that is going to be very important. Second thing is the behavior on the non-starving writers. Okay, so we said we had a problem in the readers and writers problem, that an additional challenge or problem in there, that writers could be blocked indefinitely. So we wanted a way to stop that from happening, and we proposed a solution for it. So familiarize yourself with that solution. And finally, you want to look at band.c in advanced I think advanced semaphores too. All right, so those are 3 things to focus on for tomorrow's exam while you are preparing for things. All right, questions about anything before we get started with today's session? Yeah, go ahead. One of you.
The advanced semaphore lab,
Yeah.
that can be graded by tomorrow, or if we have questions, can we like how we did on certain things, can we like email you?
If you have questions about your solution, then probably I doubt that the grader will be able to go through it entirely today. So probably office hours tonight is the best place to go for that. Yeah.
On the exam, if you give us like a problem that requires us to get like 2 non-starving writers, how would we test if it's starving or not? Because it's like maybe one case that's get them starving.
Yeah. You have to convince yourself that it's non-starving. So basically, think about it as the way that your scheduler is your enemy. And then what's the worst thing that can happen without your solution? Like, and does your solution stop that? The other thing you can do is try to run your problem without your solution a few times. Generally, you're going to see the pattern emerging that, for example, in the readers and writers problem, we have 10 readers and 2 writes and a bunch of reads. And this means that you probably have a problem in there, and then you can start out. Okay. Other questions? All right, so today we're going to continue our review of the material for tomorrow's exam. What we're going to do is we're going to re-review these 2 problems. So we're going to rethink about the readers and writers problem. Remember what we did in there. Focus on the patterns of thought that we had in there. And then we're going to try to pick up where we left off on exam 2 of 2020 and solve a few more problems in there. Okay? So let's go ahead. Can someone remind us what the readers and writers problem is? You should have memorized it by by now. So what are the key components of the readers and writers problem? Yeah. Yep, exactly. Simply as we have a shared place in memory, we have two types of threads. Readers that are reading from the shared place of memory, and we have writers that are modifying, updating this place in memory. Okay? Now, we said the first thing we said is that if we think about just the readers without the, yeah, go ahead.
I just want to add that concurrent access is allowed, but you can't concurrent modification.
Yeah. So pretty much that's what that's the problem is that we have concurrent reads and concurrent writes to the same place in memory, which creates a race condition in here on our memory. Okay, now if we were just doing readers by themselves, we wouldn't have a race condition because readers just read the value of the data. They're not going to update anything. They're not going to change anything. So we're pretty much in good shape in that. The problem comes about that when we add the writers back into the gameplay, and that's when problems arise. And we said we had two race conditions. One is race condition between writers. So if more than one writer is trying to update our shared space or shared variable, we're going to have concurrency issues. There is a race condition. Second one is a race condition between readers and writers. So if I'm trying to write somewhere, there shouldn't be anyone trying to read from that same spot at that same time. Okay, so we said our first solution was basically just to lock this whole thing up. Right, if you recall, we said initially, intuitively, you would be inclined to say, well, I'm just gonna lock or wait on a semaphore before I access the shared memory, whether it's reading or writing, and I'm gonna post to that semaphore after I'm finished reading or writing. So protect the critical section with a semaphore. And we saw that once we ran this, that the problem was, well, we didn't allow multiple readers at the same time anymore, because the readers between themselves have no race condition. The race condition is either between the writers themselves or the writers and the readers. So if I had multiple readers at the same time and no one writing, I should be able to allow those into my critical section. And the problem was that we were no longer allowing that behavior. So we wanted to solve it. So can someone remind us, how did we solve this problem? So how did we allow for multiple readers to enter the critical section at the same time if there are no writers in there? Yeah. So
We could assign up saying like writers staying out, like whenever the first reader to go in, but something sign and the last one to come out.
Yes. So remember this pattern very, very, very closely. The first person or the first thread that went, the first reading thread that went into the critical section, put up a sign that says readers are inside. Now, writers, when they came in and they saw this sign, they would wait. And then when writers, when they come in and see the sign, they're going to wait. Readers, when they come in and see the sign, they're still going to come into the critical section. So remember, we used the analogy of we had a party going on, and we wanted students to go into the room to party, but the janitors basically wanted to stop the janitors from going in while students were in the room partying. Right? So the first student that goes inside puts the sign. The last student that's going outside takes the sign there. So let's take a look at how the source code for this one look like. So or pseudocode for this one look like. So we had a semaphore that we called, so we need a mutex, and I think we called the other one party. And we wanted to count the number of readers to make sure that we know if I'm the first one in or the last one. So the first thing we did is we tried to lock the mutex. So we did await on the mutex. And then we incremented an R. Then we checked that if NR is equal to 1, then so this is first one in. This is going to do await on party. Okay, and then after that, we post to the mutex, and we enter the critical section. Okay, so at the other end, we did the same thing, but in reverse. We wait on the mutex. I decrement an R, and then say if an R is 0, then this is last one out. Then I wait, or I post to the party. And then unlock the mutex. Okay. So, see this behavior in here? Memorize this pattern of behavior. You should be able to, once you know that you need a behavior similar to a readers and writers problem, you should know that something similar, you're going to have something that's similar to this that looks like the following. You increment a number, you check if it's the first one in. If it's the first one in, you're going to have to wait on something else. If not, you just release the mutex and then you go. Now, a question is, so before I ask the question, let's just write down what the writers do. So here they're going to wait on party, enter the critical section, and then post to the party semaphore. Okay. So a question for you is the following. If I have a writer in my critical section, or if we want to think in terms of the analogy, if I have a janitor inside of the room, and I have 5 students that arrive to enter the party, how in this code are we making sure that those students are not going into the party, are not going into the room? How is this code ensuring that all 5 of them are waiting for the janitor to finish up? Yeah.
That's why you have the top mutex, right?
Okay. So are they all going to be waiting on this top mutex?
Because the first, no, everyone but the first one.
Yes. So remember that the first one is going to go in here, and first one blocks here, and then the other ones block here. Okay, so it's not necessary that all of your waiting readers are waiting at the exact same spot. When you post to the party mutex, one reader is going to continue from here, other readers are going to continue from down here. Okay, so always keep in mind who's waiting where and what are they going to do when they wake up. If you want your first one in to behave differently than the other ones when they wake up, then this is the place to add your code. Okay? Questions? Okay. So what did we say the problem with this, or did we say what did we say we have what problem is this with, is there with this solution? Are there any things that we should worry about when we're doing this type of solution? Yeah.
As long as more readers keep coming, the writers are never going to be able to write. We're starving.
Yes. So the problem we're concerned with is the problem of starvation. And this can happen in the following condition. If, let's say, I don't have writers initially, so readers take the room, readers take the critical section, and they never stop coming in. So all I have is readers coming in, readers coming in, readers coming in, and then a writer arrives. That writer is stuck there forever. Right? If readers keep coming in, as long as readers are coming in into this code, the writer will never enter the critical section. So that was the same problem when we said if the entire university students are coming into this party, the janitor might not be able to ever clean the room. Okay? So how did we solve this problem of starvation? What was the solution for this problem of starvation? Yeah.
And I can't remember what it was, but we added another sim tech or sim before that. Whenever the writer, whenever the writer wants to go in, it locks the door so no other readers can get in.
Yeah. Avi, do you have anything to
I
add?
have a question.
Okay. Go ahead.
With the writers, so if a writer does come in and there are readers waiting, not waiting on the party, but waiting at the unit.
Yeah.
Does it just say, burn all that, I want to go in? And like, so it just goes in while there are people waiting in the units?
So the only chance that there will be people waiting on this mutex is there is a first one that's waiting here. So if there's one waiting here, this means the writer is already in the. Does that make sense? No. So the solution for our starving writers was we did something as follows. We said that we're gonna, when the writer comes in, they're gonna pretty much lock the door to the room. And then they're not gonna allow any new readers to come in. So when the janitor wants to clean the room, they're gonna lock the door from the outside, and they're gonna prevent new students from joining the party. But it still has to wait for the other students to leave. So it's gonna wait for whoever is inside now, but it's not gonna allow any new students to come into the room. Same way here. When the writer comes in, they get a priority over the readers. So no new readers can come in, but the old readers, the ones that are already inside, are gonna continue until they leave, and then the writer comes back. So the way we did that is we added a third semaphore. I think we called it door. And then the reader is going to try to wait on it. And then as long as it is in its critical section, it's going to hold the lock or keep the door locked until it is done before posting back to the door. So what did we do in the reader's end? Yeah.
Don't you put a wait and post on the door back to back so it like continuously reads those?
Yes, exactly. So what we did is that we said we wait on the door and we lose our projector. There we go. And then we post on the door right away. So why did we do this wait and post back to back? What was the reason why we did this back to back? Yes.
Many times. If you wait, then you just check and see if the door is open or not.
Yeah, exactly. Because all we need to do is check if the door is open or not. If it's not, we wait. If it is, we just go in and close the door back out, right? So that's exactly what we were doing. So in other words, these two lines, they do not protect any critical section. So between these two lines of code, there is no critical section. There's nothing happening between those two lines because that's not the intention of why we added those semaphores. This is a semaphore for priority enforcement. So we only use this to enforce the priority between the readers and the writers, but we're not actually creating a new critical section. We're not protecting any variables from updates or concurrent reads or concurrent updates. So that's why it is safe for us to just do wait and post in here, wait here and post in here. Yes?
It's used for priority enforcement.
Yeah, it's just used for priority. Questions? All right. So that is our review for the readers. Yeah.
Does the order of the post statements in the writer matter?
Yes. So the order of the post statements in this specific example, it doesn't. But generally, the rule is last, wait, first, post. Okay? So in a sense, in this specific example, pretty much no change is going to happen. But generally, you don't want to change the order of things because in semaphores specifically, sometimes the order matters, sometimes it doesn't. Sometimes you want a specific order to unlock things. Sometimes you don't. If you don't, last wait, first post. If you know exactly what ordering you need, then you just follow that specific. Other questions? Okay. So with that being said, let's jump back into the exam and see what else do we have in here. So I believe we already did parallel add. I think we touched on road.c. So I will continue from downloads and polite threads, and that would kind of complete this exam. So let's take a look at what we have in downloads. Is this visible, or should I try to change the colors a little bit? Good. Okay. So we have a system that downloads data into slots in an array, right? So we have downloading threads. They go into specific slots in an array, and they just download stuff into those slots. And the way they do that is for a few constraints we have on top of it. it is necessary for the system that downloads proceed in parallel. So we must have all downloads happening at the same time because they're going to be downloading to different things. When a downloader downloads, it picks the first available slot to write to. Okay, so if I am the first downloader, I should put my stuff in slot 0 in my array. If I'm the second downloader, I put my stuff in slot 1, and so on and so forth. But the constraint is that two downloaders should never use the same slot. So we need to use semaphores to ensure that downloaders download to different places and not the same slot. Okay. Second thing is the readers come in and they read a particular slot of data. So reading is fast, so it's okay if reads don't happen in parallel. So it's okay if reads happen sequentially, but a reader should never go in and read before something is downloaded. So if nothing is downloaded yet, the reader is blocked. As long as the reader nothing is downloaded yet, the reader will remain blocked until something is downloaded into the slot it wants to read. So we can visualize this as follows. We have an array of things. We have downloaders, and they're going to download different spots. These have to happen in parallel. We have readers that are going to take things out, and we can have multiple readers from the same spot. So we might have something like this. So we might have 3 in here, or maybe 1 in here and 2 in here. Okay? So how do you suggest we enforce the constraints that we have in this problem? Any ideas of how would we enforce these constraints? So I'll give you about 3 minutes or 2 minutes to think about this problem. If you want to start, if you want to open up your code, this is in sample exams, exam 2, 2020. No, we're back. All right, any thoughts or ideas how we would proceed? Yes, Dave.
So what we can do is we can have a global variable. I was thinking maybe have a global variable. Use the curse slot that's in there.
Yeah.
And like for the downloader, whenever it's going to mod, like what it does is it like waits for the critical section, and when it enters it, saves that to a local variable, and then increments, then it can leave the critical section, and then it can do the download without having to worry about like having another critical section to read from it because it saved it off to a local variable.
Okay, so that's how we coordinate the readers doing things in parallel, right? So let's go ahead and do that. So we're going to have to add a mutex. So I'm going to write everything in terms of semaphores because we said previously that you can assume that you can solve everything on the exam using semaphores. So this assumption still holds, so that's why I'm just gonna use semaphores throughout, but you can use any other form of concurrency management you want.
Partly done.
Yeah, so it's already written for you. It's the only thing you have to do is write the concurrency form, right? So let's initialize the semaphore. Mutex 0, 1. So remember that when we initialize the semaphore to act as a mutex, normally we initialize it to be unlocked, so we initialize it to 1. Okay, so what we're going to do is we're going to protect this part with our mutex. So we're going to wait for mutex, and then we're going to post to our mutex. Okay, so now how do we protect? We solved this issue, that we want our readers to go in parallel and write at different slots or different spots. How do we solve the readers issue? That we want our readers to wait until downloads are ready and then they start reading. Yeah.
This was kind of said in the comments, but like you could have each slot have its own semaphore the weights on and post to when someone can download and read it, know from that slot whether they can read.
Yeah, exactly. So we're going to have one semaphore for running out of colors. Run one semaphore for each slot in here and protect each slot with its own semaphore. So this way we can still ensure isolation between the writing threads, but we ensure that reading threads are waiting for the writing threads. So let's go ahead and do that. We're going to have a, let's call them read sems for each slot. So we're going to ask writers to my slot and post to it when they're done. And the same thing happens for the readers. Okay, so let's try to initialize those mutexes. So what do you think the initial value of these semaphores should be? Yeah. Okay, so if we initialize it to 0, what's going to happen here? Hold on to that thought, because I know where you're going. Yeah.
Are we assuming that the downloads can have, like, you can re-download to the same slot? Because if not, if you could set it to 0 and not have the wait at the beginning for
Yes.
download?
Yeah, exactly. So that was the trouble that we were in now. Because if we initialize this to 1, and we try to do this, then we might end up in a case where a reader arrives before a writer. and it's going to take over this critical section and read without waiting for the downloader to finish downloading. So what we're going to do is we're going to do the opposite. We're going to use this as starting from 0, and then the reader, the writer itself, the downloader, doesn't really have to wait for it, right? Because it can jump ahead and write either way. It doesn't have to wait for anything. The only thing that it has to do is tell the readers that they can now go in and read the stuff. So it is only the readers that are waiting on these semaphores. The downloaders really don't have to wait on those semaphores. And that is how we avoid the problem of having a reader arriving before a writer and then not blocking. Because otherwise, if we initialized our semaphores to 1 and the reader arrives before the writer or before the downloader, we are in trouble. Okay? Questions? Yeah.
I know that like concurrency for the readers doesn't really matter, but could we just like wait and then post right away in the reader because it's not a critical section, so that multiple things could read it?
Yes. Yeah. You could definitely do this. The only thing that this is saved by the fact that we only write once. If we didn't write once, then our whole setup kind of breaks apart. Yeah, but if you want to avoid the concurrency, then you can definitely do that. Other questions? Okay. So this concludes downloads.c. So let's go ahead and take a look at polite threads.c. So this is, I think, that was the most challenging problem in that previous exam. And it goes as follows. Let me just quickly jump to the diagram to save time. We have a critical section that's protected by one semaphore or by a semaphore. So we have a semaphore wait happening in here and a sempost happening at the end. Okay? Now, the only difference is the following. We have two types of threads that are coming in. Threads of type A, threads of type B. And if, when we post, we have two cases. If the number of A's waiting is greater than the number of B's waiting, or greater than or equal, then we let A's in. And similarly, if B's waiting is greater than A's waiting, then let B's in. So instead of a normal semaphore, the way it behaves, it does first in, first out, we're going to have to implement something that says the one that has the more waiting threads is the one that's going to go in. So if I have more A's waiting than B's, the A's are going to go in. If I have more B's waiting than A's, the B's are going to go in. Okay? So I'll give you a minute or two to think about this so we can try to solve it in time before we have to conclude our session. Okay, so any ideas how would we approach this problem? Yeah.
I don't have it completely, but I have a general, like, we'll need it.
Sure.
I was thinking about using a scoreboard for A's weighting and B's weighting,
Mhm.
and then we'll need 3 semaphores, one for the CS itself, and then one for A's and one for B's.
Yes, exactly. So we're going to do something along the lines of simulating that behavior using 2 semaphores instead of just one. So there's 1 semaphore for A's, 1 semaphore for B's, and a third semaphore to protect any critical sections we're using for the scoreboard itself, right? So we're going to remember how many A's are there, how many B's are waiting, and then the A's are going to be waiting on a different semaphore than the B's. And that's the trick, is that there is 1 semaphore here and another one here. Then when I want to post to this virtual semaphore, if the number of A's waiting is not larger than the number of B's waiting, I post here. If the number of B's waiting is larger than the number of A's waiting, I post here. Okay? Now there's one thing that we haven't thought of yet. What happens if I arrive and there's no one waiting? What should I do? What are the 2 possibilities that might be if I arrive, there's no one in the queues for A and B? What are the possible things that might be happening at that point?
Be the first or the last.
It's close, close. So you're either at the first in the sense that you just want to go in exactly into the critical section. The other option might be that there's already someone in the critical section, but no one is waiting. So the person or the thread in the critical section was the last thread waiting, and you're the first one to arrive after. So in that case, you have to wait. But in the first case, you didn't have to wait. So let's put it another way. If the number of A's equals 0 and number of B's equals 0, then this either means that one critical section is empty, 2 critical section has exactly 1 thread. So there's either 1 thread in the system, and that is inside of the critical section. There's no one else waiting, or there's nothing in the system. Those are 2 implications of having the number of A's waiting and the number of B's waiting both being 0 at the same time. Okay, so this is the solution we're going to have to implement. If I am the first one coming in and I see that there's no one waiting, then I have to check, is there anyone inside of the critical section? If no one is inside the critical section, then I just go inside and just do nothing after that. If, on the other hand, I go in and I don't see someone in the critical section, or I see someone in the critical section, then I have to wait on either of my corresponding queue. So if I am an A type, I go into the A waiting queue. If I am a B type, I go into the B waiting queue. So let's go ahead and take a look at the source code. Because we're running out of time, we're not going to type the source code. I'm quickly going to walk you through the solution that we have. So as we said, we're going to use 3 semaphores, 1 to lock any variables that we have race conditions over, 1 to be for A's waiting queue, and another third one to be for B's waiting queue. What's going to happen when we first go in is that we're going to keep track of whether there is someone in the critical section or not. And if there's no one in the critical section, I will set the flag in critical section to true, because I am in the critical section now, and unlock anything I had in hand. Otherwise, if there is someone in this critical section, so in critical section is already true before I come in, then I'm gonna, if I am of type A, I'm gonna increment the A's, post to the mutex, and then wait on the corresponding A key. Exactly the similar behavior for threads B of type B. I wait on the mutex. If no one is in the critical section, I set the flag and I go into the critical section. Otherwise, I have to wait, increase the number of B's waiting, and wait on the B key. Does that make sense so far? Do we have any questions? Okay, so posting now is going to be different. So that's why we created this function called pick thread to release, which we're going to call instead of the posts. And here's how it goes. We're going to grab a new text lock because we're going to be modifying global variables. And we're going to do the following. If there are no more waiting stuff, so I am the last one leaving. This is the post, remember. I am the last one leaving and there's no one waiting, then I reset the critical section to be false. Okay? Otherwise, if there are more A's, more or equal A's than B's, I'm going to decrement the number of A's waiting and post to the A queue. Otherwise, I decrement the number of B's waiting and post to the B queue. And finally, at this point, release my lock. Okay? So 3 things I should check. Am I the last one out? If yes, then just set the flag. If not, then post on the corresponding queue. So questions for you before we leave. The question is, if both queues are empty, we are not posting to anything. We're not incrementing the value of any semaphore. So how do we make sure that the first one coming in can actually go into the critical section? Because at this point in time, if both count A's and count B's are 0, then we're not posting to anything. So all our semaphores, semaphore A and semaphore B, both have 0 values. So how do we make sure that the first one, how are we making sure that the first one comes in? Yeah.
We make sure the in critical section variable starts at false.
Yes, so we're setting in critical section to false. And if you can notice here, when we are in the case where in critical section is false, we don't have any waits. So we don't have to wait anymore. So that's why it's okay for us not to post to a semaphore. In fact, it's correct not to post to a semaphore, because if we post to a semaphore, we would have made our problem wrong, or our solution wrong, in a sense. Okay, questions? So, we have 1 minute left, so all I have to say is focus on the readers and writers problem, the behaviors that we talked about, band.c, this guy. If you have more questions, I have office hours 5 to 7 p.m. tonight. So just drop in on Teams, and that we can chat and talk.
I had a quick question.